Kabir, can you send a message that everyone to join quickly?
Yes, it is. आप लोग टिके पार्टी करी उनका Titapa?
Yes, sir.
Okay. Are you ready?
Yes, sir.
Sir, shall we start?
Yes.
Okay. Good evening, all. I, Dr. Prabir Kumar Shetty, welcome you all to the second session of this atal FDP. That is 2 weeks of the faculty development program on the architecture design of the VLSI. So today, the invited speaker is Professor Shaik Rafi Ahmed from IIT Guwahati. Now I request our student Brutitapa Misra to introduce him. Brutitapa.
Good evening, everyone. I am Brutita Mishra. Welcome you all in the second week faculty development program by AICTE Training, Learning and hosted by SUIIT. It's my pleasure to introduce Professor Shaik Rafi Ahmed. He completed his MTech in Electronics Instrumentation and Communication System from Sri Venkateswar University College of Engineering, Tirupati. He received his PhD degree in Electronics and Electrical Communication Engineering from IIT Kharagpur, India. He is presently working as a professor in the Department of Electronics and Electrical Communication Engineering at Indian Institute of Technology, Guwahati, Assam. He has required more than 30 years of teaching and research experience. He guided and successfully completed 7 PhD and 9 candidates are going on. He has published more than 35 research papers in reputed journals and more than 60 research papers in reputed conferences. He has served as a reviewer of many IEEE transactions, IEEE letters, IEEE journals, and other reputed journals. He received Outstanding Reviewer Award in Jan 2019 by Elsevier Digital Signal Processing Journal. He also received Outstanding Reviewer Award in Jan 2017 by Elsevier Biomedical Signal Processing and Control Journal. His research interests include VLSI architectures for signal processing algorithm, digital signal processing, and biomedical signal processing. Thank you. And now it's over to you, sir.
Thank you. My screen is visible?
Yes, sir.
Yeah.
So welcome to this session on efficient DSP algorithms using hardware. There are two possibilities. One is you can use the general purpose the systems such as the microprocessor, microcomputers. So the other one is application specific integrated circuit. So the drawback of this general purpose computation is, so they are programmable, but this is cost efficient for general computing, not for specific these DSP applications. So if you want to perform the, say for example, the filtering operation, you have to write the program. And if you want to perform the transform, you have to write the program. Whereas in case of application specific integrated circuits, so you can design the hardware corresponding to whatever the operation that you want, like filter and transforms. So because of that, so this application specific integrated circuits based realizations or based implementations are more accurate and fast, and also more cost effective when compared with the general purpose implementations. So the examples like FFT chip, as I have told, in case of software based implementations using general purpose systems, you have to write a code for this FFT. Whereas in case of ASIC, we can fabricate the FFT chip, similarly the filter chip. That is why this is more suitable for the real-time applications. So if you want to, develop ASIC architecture for a given signal processing algorithm, so what are the steps need to be followed? So this is the ASIC, basic ASIC design flow. So first we will be given some specifications. So this is what is called algorithmic level. Then from the algorithm we will map onto the architecture. This is called RTL, register transfer logic level. Then the architecture we can implement by using the logic gates. This is called gate level. And inside the gate we have the circuit, which is called transistor level. Then the transistor basically consists of a device. So after that we'll come with the layout. So this layout will be sent to the foundry for the fabrication. So these are the different levels of this ASIC design flow. So starting from the algorithm to architecture, gate level, transistor level, device level, and then finally layout. Now in order to design a IC for a particular application, so what are the factors that you have to consider? Is the primary factors are speed, area, and power. You have to design the IC which can operate at high speeds, which occupies less area, which consumes low power. But here there is some sort of trade-off between these three parameters. So the speed, power area, speed power product is constant. So if you want to increase the speed, at the same time the power also will increase. Faster circuits dissipate more power. So there will be some compromise. So but here the design challenge is to have a better trade-off. Cannot increase both the speed and you cannot reduce the power simultaneously, but you have to have a better trade-off. Okay? So in order to have this optimization problem, so which will give the optimum speed, optimum area, optimum power. So you have to optimize the problem at each and every level. If you go back to this the design flow of ASIC, the different stages. So you have to optimize the problem at algorithmic level. You have to optimize the problem at architectural level. You have to optimize the problem at gate level, transistor level, even at the layout. So once if you optimize the problem at each and every level, finally you will get a IC which can operate at high speeds, which occupies less area, which consumes low power. So here the optimization at different levels I will explain with some examples, and in this presentation mostly I will concentrate on the optimization at architectural level. So this is something like so the system to the device, this design flow, starting from the algorithm to layout. This has a resemblance with some continent. The part of the continent is country, part of that one is state, part of that one is district. Like that, it will go up to brick. Similarly, system, subsystem, functional unit, flip-flop, gate, transistor, and device. So this hierarchy is similar to that of the continent to brick. Now coming for this optimization at different levels. The first level is what is called as algorithmic level. Okay. So the example here is computation of a discrete Fourier transform. So we know that if you use the direct formula for the discrete Fourier transform, it takes n square complex multiplications. Whereas if you use the FFT algorithm, decimation in time and decimation frequency algorithms, so we can reduce this number of complex multiplications from n square to n logarithm n to the base 2. This is always less than n square. Even after some optimization, even you can reduce this to n by 2 log n to the base 2 also. This is what is called the optimization at algorithmic level. If we take another example of a sum of natural numbers. So if we add these numbers 1 to n, so this requires n minus 1 additions. If we want to add 3 numbers, we have 2 additions. Like that, if we want to add n numbers, n minus 1 additions. Then if you use this direct formula, whereas this s can be represented in another way as n into n plus 1 by 2. If I use the second formula, then we require one increment operation n plus 1 and then one multiplication, one division. Of course, this division by 2 is basically a shift operation. So in some cases, actually, if the number of n value is large, then the second way of implementation is more optimal when compared with the first time of the implementation. Okay. So this is what is called the optimization at algorithmic level. If you go for the optimization at the second level, which is called as architectural level, if you take the if you consider the same problem of adding the first n natural numbers. So there are two algorithms. So these two algorithms will add the first n natural numbers. So here we are going to input n. So how many numbers you have to add? So you initialize the register with a 0. Then for I is equal to 1 to n, you increment this s. S becomes s plus I. Then you input the next I. So like that you proceed until this I is equal to n. So then once if you add all the n numbers, then you have to output s. So initially s is 0. So 0 plus 1 will be added, s becomes 1. Then 1 plus 2 will be added, like that. 1 plus 2 plus 3, so on up to n will be added. Now if we map this algorithm onto the architecture, what are the corresponding architectural blocks required to realize this algorithm? Is we require a register to store the n value. This input n value, this is a register. And we require a counter which counts from 1 to n. This I is a counter. This is modulo n counter. The modulus of this one is n. And there is one more register s which stores the intermediate results and also the final result also. We have to update this register every time. So initially I'll feed this n value. Say if you want to add first 10 numbers, I'll feed this with 10. Then initially I will make this I as this is a counter which counts from 1 to n. So normally the counter will start from 0 to a particular value, but initial value of this counter can be initially to 0001 using clear and preset signals. Okay. So initially I'll make this counter as a count, initial count as 1, and then it will increment up to n. So this n value will be compared with I. If I is equal to n, we'll stop. Initially I is equal to 1, we'll compare with n. Say n is equal to 10. So this is 10 and this is 1. So this is larger. So the output of this one is, this is a comparator. This can be output can be 1 or 0. If both the inputs are equal, then output is 0. If n value is greater than I, output is 1. So this 1 value will activate this s. So the sum value, which is, this is adder basically. So this adds I plus s. The initial value of s is 0. So this is 0. Initial value of I is 1. So 0 plus 1 will be added. Sum is 1. That will be stored back into the register s. Then the second value is 2. 2 will be added with S is 1. So 2 plus 1 will be stored back. So like that, this will, when this I becomes n, so these two will be equal. This will be added. After that, the output of the comparator will goes to 0. It will stop this register. It will skew this register. And if you read the value of this register S, that will be sum of the first n natural numbers. This is the architecture. Here, what are the different architectural blocks required? Is one comparator, one adder, 2 registers, one counter. So if I want to optimize this architecture, so I'm going to modify this algorithm slightly so that I can get a simplified architecture. So if I take this, if I have a look into the second algorithm, this also will perform the same addition of the first n natural numbers. So here also I'm inputting n, s also 0, first two statements are same. But here instead of counting this in the up manner, 1 to n, we are going to count from n to down to 1. Instead of 1 to n, now it will be n to 1. Then s is equal to s plus 1, s plus I, then next I, everything is same. The only difference here is instead of counting in the up direction, we are going to count in the down direction. Now if I map this algorithm onto the architecture, so here also we require the I which is down counter, the complexity of the up counter or down counter are exactly same. There is no change. And this S register is same. Now here I don't need the register to store this n value. So why? Because initially I load this I with n using preset and clear signals. After that I don't need the n value. What is that we want is whenever this counter comes to 1, I have to stop this counting. Okay. So for that we are going to check the OR gate. The output of, if this is say for example 4-bit counter, so we'll connect 4 input OR gate here. So the output of the OR gate becomes 0 if all the inputs are 0. Means up to 1 it will count. After 1 the down value is 0, 0, 0, 0. Whenever it comes to 0 it will stop. It will squeeze this counter. So whatever the value that is present in the S is the sum of the first n natural numbers. Now if you compare the computational blocks of these two architectures, here we are not using the comparator. And this register, instead of register, we are using just simply OR gate. So with respect to the complexity, this is having a less complexity when compared with the first architecture. So this is an example of optimization at architectural level. So in this presentation, we'll discuss some more DSP algorithm. This is a simple problem. So here we are going to discuss the various DSP problems such as filtering and transforms, and how to optimize at architectural level, that we are going to discuss in the coming slides. So this is the second example of optimization at architectural level. So what is the next level? Next level is the optimization at logic level. So if you take this 2x1 multiplexer, so this is the truth table of 2x1 multiplexer. There is a selection line. Selection line is 0. The output should be A. If selection line is 1, output should be B. There are 2 inputs, one selection signal. So you can easily check this truth table for this circuit. This is the implementation using AND gate, OR gate, NOT gate and OR gate. So we know that if I want to implement this using the CMOS gates, because CMOS implementation is more advantageous than the transistor based implementation, even NMOS, pseudo NMOS and pseudo PMOS also. So if I take the CMOS gate implementation, we know that inverter requires 2 transistors, MOS transistors, and AND gate requires 6, because AND gate is a NAND gate followed by NOT gate. NAND gate can be implemented by using a 2 input NAND gate with 4 MOS transistors, then inverter with 2, total 6. If you count the total number of transistors, this is 20 transistors. Whereas if I use this universal based logic, if I implement every gate with only NAND gate, you can easily check that this also will give the same truth table. So if I replace all the gates with the NAND gates, now we require only 14 transistors. So we are reducing the transistors from 20 to 14. This is what is called the optimization at logic level. This type of optimization you might have studied in your digital logic design. And the next level of implementation is circuit level. So at the transistor level also you can you can have the optimization. If I take the same 2x1 multiplexer, here I require 14 transistors. Whereas if I use the transmission gate logic instead of CMOS, I can implement using only 6 transistors. Here there are 4 transistors. To get S bar from S, I require an inverter. For that we require 2 transistors, total 6 transistors. So we are reducing this number of transistors from 20 to 14 using the optimization at logic level. Optimization at transistor level, we can further reduce to 6 transistors. This is transmission gate logic. This also will perform the same operation as that of the 2x1 multiplexer circuit that we have represented here. Then finally we can have the layout. This is the layout of 2 input NAND gate. Here also we can do some optimization like placing this VSS and VDD near the input terminals and all. So by using that you can reduce the length of the wires. You can have this optimization at layout level also. So these are the different optimization that you have to perform at different levels. So finally, after optimizing the problem at each and every level, so if you fabricate the IC using this layout, then the IC will operate at higher speeds, occupies less area, consumes low power. So this is about a brief background of this ASIC design flow. So in this presentation, I will mainly concentrate on optimization at architectural level. The other optimizations normally will be studied at different BTech level courses, but in most of the curriculum, this optimization at architectural level is missing. So here in this presentation, I will concentrate on architectural optimization techniques. So there are different architectural optimization techniques. So one is pipelining, parallel processing, unfolding, retiming, folding. So these are the various architecture optimization techniques which uses the multipliers. So after this, I'll discuss about some architectures where the multiplier is replaced with shift and add operations or some other blocks. Okay, that is called multiplier-less architectures. So first I will discuss the pipelining. So this is the common terminology used in this pipelining. Iteration is defined as the execution of all the computations in the algorithm once. And the throughput, which is the indication of the speed, is nothing but sampling rate, the number of samples processed per second. Then we have the critical path. This critical path is an important term which is going to decide the speed or throughput of the system, which is defined as the computational time of the longest delay-free path. Even though this is path, but this is time actually. This is loosely called as critical path. But the correct term for this one is critical path time. The units of the critical path is second, not the distance. Okay. This is defined as computational time of longest delay-free path. And latency is defined as the difference between the time at which the output is generated and time at which the input is received. This is some sort of delay. Okay. So if I consider a 3-tap FIR filter, this is the mathematical difference equation of the 3-tap FIR filter. Y of n is the output, x of n is the input. So coefficient A into x of n, B into x of n minus 1, C into x of n minus 2. This is the relation. This requires 3 multipliers, 2 adders and 2 delay elements. Now we are going to feed the samples because DSP problems are non-terminating type. Like if you take the mobile, so we have this the equalizers and all filters will be there. So the data will be continuously received on the mobiles. So DSP programs are called non-terminating type because the data will come, infinite data will be there. This is first sample, second sample, third sample like that. So infinite samples. For every TS seconds, one sample will feed into the circuit. Now the question is, how fast your circuit or the filter can process the samples? If I feed the first sample, so what is the minimum time that is required? Or what is the maximum time that is required to feed the second sample? If this TS is less, I can call that the circuit is faster circuit. So this TS should be very, very less so that it can process more samples per second, means throughput is more. Okay. So I have to design the circuit such that this can process more number of samples per second, means the throughput of the system is more. Now, who is going to decide the spacing between two successive samples? Is this critical path. So which is defined as the computation time of the longest delay free path. So here if I consider this particular 3-tap FIR filter, this dashed line, here there is no delay at all. So there is a multiplier, one adder, another adder. So this total computation time of this delay free path is Tm plus 2Ta, where Tm is the multiplication time, Ta is the adder time. So means now this Ta should be at least Tm plus 2Ta. I cannot feed the second sample before this Tm plus 2Ta. Otherwise what happens is there will be overlapping of two successive samples. So this I cannot increase the throughput of the system beyond this Tm plus 2Ta. This is the time delay and throughput is 1 over Tm plus 2Ta. This is the original system. Now how to increase the throughput or how to reduce the critical path of the system. So for that the first technique is called pipelining. In pipelining basically we are going to place latches along the some cut set. So for example, if I take this 3-tap FIR filter problem, so these two latches are additional. So I am placing two latches, this latch and this latch. The remaining entire circuit is same. Now what will be the critical path? So if I come from this multiplier to this adder, and there is a delay here, so this is one multiplication and one adder time. Or even if we consider this also one multiplier, one adder. If you consider this also one multiplier, one adder. Now the critical path time is Tm plus Ta only. So because of placing these latches here, so I am reducing the critical path time. So in the previous case, this duration is Tm plus 2Ta at least. Now in the second case, this is pipelined system, pipelining of the FIR filter. Now here the samples I can feed the first sample. After Tm plus Ta itself, I can feed the second sample. So in that way, if I compare these two circuits, so compared to this circuit, this is faster circuit. This is having larger throughput because this can process two successive samples with a less delay, which is Tm plus Ta. But here the thing is we are placing the samples here. So what about the functionality of the system? Okay. You can place the samples. We cannot randomly place the samples at any point. Okay. We should have some rule to place these latches such that the functionality of the system should remain same. If the functionality changes, even if you increase the throughput of no use. Okay. So in order to retain this functionality, you can easily see that by introducing two delays in the two parallel paths. We can find out that if I call this as y dash of n, this is y of n minus 1. You will get the same function, whatever this yn is a into x of n plus b into x of n minus 1 plus c into x of n minus 2. Now here you will get this output as a into, you can see here, this is x of n minus 1, x of n minus 2. So we'll get a into x of n minus 1, b into x of n minus 2, c into x of n minus 3. So we'll get the same expression, but here this becomes n minus 1, this becomes n minus 2, this becomes n minus 3. So means if we call this output as y dash of n, this is y of n minus 1. Means the system functionality is same, only the output is shifted by 1 unit. This is called latency. Latency of 1 clock period will be there, but XOR the values will be same. Whatever the values that will be given by this system here, suppose if this gives 1, 2, 3 outputs, this also will give 1, 2, 3 output, but with a delay of 1 clock period. So as a result of that, so this system is having a latency of 1 clock cycle that I don't care, but the critical path is reduced from Tm plus 2Ta to Tm plus Ta. Because of that, the throughput will increase. Now for the simple systems like this 3-tap FIR filter, by observation I can know where this latches has to be placed without changing the functionality. Suppose if you have a big system, complex system consisting of hundreds of the multipliers, hundreds of the adder, then how to find out the exact location where this latches has to be placed without changing the functionality of the system? Yeah. For that, we will follow a rule called as cut set. Here actually I have explained why this is called pipelining. This pipelining actually this is similar to this. If I take the water pipe, you throw a stone here first. So when the first stone is in between this pipe somewhere here, you throw the second pipe, second stone also. Okay. Means you are crossing more than one samples per second. Okay. That is why the name pipelining. So in the cut set pipelining, so this will give whatever the complex system is, the place where we have to place the latches without changing the functionality. For that, we'll define as cut set as a set of edges of the graph such that if these edges are removed, then the graph becomes disjoint. And that cut set is called feed forward if the direction of all the data points are in the forward direction. This will be clear in the next example. So here I am not considering this system block diagram approach. This is block diagram approach. So we know that any system can be represented by using block diagram as well as signal flow graph. So this is signal flow graph representation. Here there are nodes and connecting edges. This is A1 is node, A2 so on up to A6. There are 6 nodes are there and these are connecting edges. This is one connecting edge. This is connecting edge. So several edges. So each node will represent one computation. It can be adder, it can be multiplier, it can be modulation, it can be FFT. Okay. If I take the complex system, so each node I will represent as a FFT. Okay. So you see the signal flow graph. Now this is the original signal flow graph. And here there are the delays, and I'll assume that the computation time of each node, this A1 node, A2 node, A3 node, so on, each one will take some computation time. I'll assume that the computation time of each node is 1 unit of the time. So normally here we'll represent the computation time by units of the time. That can be microseconds, nanoseconds, picoseconds, but normally here we'll follow the notation of unit of time. Okay. Now what will be the critical path in this? Which is the longest delay free path. You can easily see that in this diagram, this A3, you start with A3, A5, A3 to A5 there is no delay, then A5 to A4 there is no delay, A4 to A6 there is no delay. So this A3 to A5, A5 to A4, A4 to A6 is the critical path. The total computation time of this one is 4 units of the time because this will take 1 unit, 1 unit, 1 unit and 1 unit. What does it mean? That the input point, if I feed the first sample, after 4 units of the time only I can feed the second sample. Okay? I cannot process the samples at a time less than 4 units of the time. Okay. Now what I am going to do is I can place the latches. Okay. So for placing the latches, you have to find out the feed forward cut set. Okay. So the second one is invalid, this one cut set. So if I take this dotted line as cut set, dotted line as cut set. So what are the edges on this dotted line? This one is one edge, this one is one edge, this one is one edge, this one is one edge. So in this cut set, we have 4 edges. And what is the direction of these 4 edges? All in the forward direction. So that is why this dotted line, these 4 edges will form a feed forward cut set. Feed forward cut set. So if I know the feed forward cut set, blindly you place the latches along the feed forward cut set. So I am placing D, 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 D. This is invalid. Here I have not placed D. So D, 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 D. Now this is pipeline version. So the functionality of this system remains same as that of this original system. Now you check this critical path of this pipelined system. What will be critical path? So if you go from A1 to A2, there is delay. A1 to A3 delay. A3 to A4 delay. Only A3 to A5 there is no delay, or A4 to A6. So critical path time is 2 units of the time. So we have reduced from 4 units to 2 units. Means you are increasing the throughput by factor of 2. Okay. So this is how we can place these latches if I have the complex system. So without changing the functionality, if you want to place the latches, what you have to do is you have to identify the feed forward cut set. Okay. This is one of the application of this pipelining is to increase the throughput, to reduce the critical path. There is a second application of this pipelining. We can use this for low power also. Okay. So in applications where the speed is not required, like biomedical applications, if you want to process ECG, EEG and all, they are low frequency signals. We don't need high speed. Okay. What is required is in biomedical, because of the portable devices such as pacemaker and all, they will be inserted inside the body. So we need low power consumption so that the battery lifetime will be more and low area. So in such applications, what we can do is pipelining we can use for lower power also. So this is something like if I take the CMOS circuits, this is the propagation delay and this is power consumption of a CMOS circuit. These two are two famous formulas. This C charge is the total amount of this charge capacitance along the charging path, that is critical path. And V0 is the supply voltage, Vt is the threshold voltage, K is the parameter which depends upon CR. Any problem?
Participant,
No,
please
sir,
on. All the participants are requested to please mute yourself. Rafi, just see that. Huh?
Yes, sir.
Okay. Professor Shaik, please continue.
Okay. So here this is the expression for the propagation delay. If propagation delay is inversely proportional to the throughput, propagation delay is less, throughput is more, and this is power consumption. So this is without pipeline. This is sequential circuit. So in the sequential circuit, so this is the the total critical path. There is no delay at all, and the supply voltage of this sequential circuit is V0. Now in M-level pipelining, as I have told in the earlier example also, we are going to place the latches. In M-level pipelining, we are going to place M-1 latches. This is M-level pipelining. This is 3-level pipelining. We have 2 latches. This is one latch. This is another latch. So now what will be the charging or discharging time? This total T sequence will be divided into 3 halves. This T pipelining is 1/3 of T sequential. So in M-level pipelining, the critical path is reduced by 1/m. Here if I take the example of this one, here I have placed 2 latches, means this is 3-level pipelining. So the total critical path is here now. Initially this was the critical path, now this is 1/3 of that. So in general, if I take M-level pipelining, the critical path is reduced by factor of m. Hence the capacitance to be charged or discharged will be also reduced by same factor. So this is the TPD and the power consumption of a sequential circuit without pipelining. With pipelining, what happens to these expressions? This is sequential and this is pipelining. So in pipelining, what happens, as I have told, the amount of the capacitance to be charged will be reduced by factor of m, because initially this much we have to charge, now only this much only. So in case of 3-level pipelining, 1/3 of that. In general, M-level pipelining, 1/m of that. Now definitely actually here this C charge is divided by m, means you will get this m factor in the denominator. So what will be the propagation delay of this pipeline system is 1/m times that of sequential, means propagation delay of pipeline system is much less, means throughput is more. But what I am going to do is, whatever the throughput of the sequential circuit that I am going to get, that is more than enough for my biomedical applications. I don't want to increase the throughput, or I don't want to increase the delay, reduce the delay. But here delay is reduced because of pipelining. So what I am going to do is here, this reduction in this delay, I am going to use to reduce the power supply. So here I am using power supply voltage of V0 to compensate for this C charge by M. So there is a reduction in the delay that I am going to compensate by reducing the power supply voltage. Instead of using V0 power supply, I will use beta V0, where beta is less than 1. If I use, say for example, 5 volts here I will use some 2 volts or 1 volt. So reducing the power supply means reduction of the power. Okay. So this, after reducing this power supply, because of this pipelining, this C charge is reduced by factor of m. So I'll reduce this such that these two will be equal. Even after pipelining also, the reduction in the delay I'm going to use to reduce the power supply. So by solving this expression, we'll get the beta value, and the power reduction will be by a factor of beta. You can see that the power of pipeline system is beta square times sequential. Beta is less than 1 means this is a fraction. So like that, you can use this pipelining to reduce the power also. So this is the first technique, pipelining. So here you have to basically place the latches at the appropriate place so that the functionality of the system remains same. Okay, I can use this pipelining system to increase the throughput, or in applications where throughput is not important, I can use this pipelining to reduce the power supply. Okay. So the second technique is parallel processing. So as the name implies, in case of a single input, single output system, so we'll feed one sample, and after some time we'll get the first sample, processed sample. Whereas in MIMO system, parallel processing is nothing but MIMO system, multiple input, multiple output system. So in case of single input, single output system, this is sequential, SISO system. We'll feed X0 after some time. If I take 3-tap FR filter, Tm plus 2Ta, I'll get Y0. If feed X1 after Tm plus 2Ta, I'll get Y1. This is sequential system. Whereas in MIMO, multiple input, multiple output system, if I consider example of 3 parallel system, 3 inputs will be fed simultaneously, and you will get 3 outputs simultaneously. So inside this also will be having this 3 such systems, SISO systems. So we are going to replicate the blocks of this SISO system here. So definitely the complexity will go high, but the throughput also will increases. Because in Tm plus 2Ta we are getting 3 samples, effectively the throughput will be increased by a factor of 3. So here for k is equal to 0, first I will feed x0 here, x1 here, x2 here. So I will feed 3 samples simultaneously. In the second cycle, I will feed here 3, 4, 5, then 6, 7, 8 and so on. But here inside this, the time taken is only Tm plus 2Ta. So after Tm plus 2Ta, here I will get only 1 output. Here we will get 3 outputs. So the throughput of this one is 3 times that of this. Whereas the complexity also thrice 3 times this one. But I can use some optimization technique to reduce this complexity, which is less than 3 times that of SISO system. That I am not considering here, but it's possible. So this is about the basic 3 parallel processing system. And if I take the same 3-tap FR filter, if I take the original 3-tap FR filter, we require 3 multipliers, 2 adders. Whereas now I require 9 multipliers, 6 adders. Complexity is 3 times that of this. But the throughput is also 3 times that of the sequential system. So here instead of using these 9 multipliers and 6 adders, I can implement this with less number of multipliers also by using some resource sharing technique. Okay? That I am not discussing here. This is about the parallel processing. So if it goes on increasing this parallel processing stages, if you have the 4 parallel processing system, then throughput will be 4 times that of the sequential system. If you have 5 times. If you have infinite blocks, infinite multipliers, infinite adders, what is the ideal throughput that we can get is infinite. So you see the case of FAR system, which is called non-iterative system. Whereas if I go for the iterative system such as IAR filter, even if you have the infinite resources, I cannot achieve the infinite throughput. And there is a factor which is going to limit this throughput, which is called an iteration bound. That I will discuss later. And I can use this parallel processing for reducing the power also, similar to the pipelining. So here this is actually this sequential system will operate with a V0. Now in parallel we have the 3 such systems. So the total the delay will be, I will make this as 3 times delay, 3 times delay, 3 times delay. If I take this average, it will be T sequential. So here I am going to operate with a lower voltage where beta is less than 1. So this will operate at lower voltage so that the decrease in this critical path time I am going to use to reduce the power supply. The same logic that I have played in this pipelining. So here if I take this sequential delay will be L times the sequential delay of the single input, single output system. So if after doing some mathematical manipulations, we'll get that the parallel processing system of the power consumption of the parallel processing system is beta square times that of sequential system where beta is less than 1. So this is a fraction only. Now what is this unfolding? Unfolding is also parallel processing. But the difference between the unfolding and the parallel processing that I have discussed here is, in the parallel processing, I have considered only the FIR filter, which is called as non-recursive filter. If I take the example of here, the output. So the output at any time depends only on the present and past inputs. It does not depend upon the past outputs. There is no feedback. There is no loop in this system. Okay. This depends upon the present input and past inputs only. That type of system is called non-recursive system. So in non-recursive system, this parallel processing is fine. Ideally, as I have told, if I have infinite resources, I can achieve infinite throughput. Whereas in case of recursive systems such as IAR filter, the parallel processing is called unfolding. So unfolding is a common or we can call it as a generalized term. So this parallel processing is a subset of unfolding. If I have the unfolding, I can obtain the parallel processing easily. That I am going to discuss in the coming slides. This is also parallel processing system only, but this unfolding is suitable for both iterative systems as well as non-iterative systems. So here I have considered a very simple example of a IR filter. Just y of n is a times y of n minus 9 plus x of n. So this not only depends upon the inputs, but also on the previous output. This is called iterative system. Whereas FIR is non-iterative system, it does not depend upon the previous outputs. There is no loop, whereas here the loop is there. Now if I consider a two parallel system, constructing the any parallel processing system for the IAR is very easy. As I have told, this three parallel system of this three pair filter. So we have to use just we have to replicate these three blocks. You can have the connections. Whereas here this is not that easy to construct a parallel processing system in case of iterative filters, okay, such as this IR filter. We see here how to construct y of 2k plus 1. If I consider this y of this is two parallel system, so 2k plus 1. 3 parallel means 3k plus 1, 3k plus 2. 4 parallel means 4k plus 1, 4k plus 2, 4k plus 3. In general, L parallel system is LK plus 1, so on up to LK plus L minus 1. So this is two parallel system. I have taken a simple example. 2k. So you replace this n with 2k, n with 2k. Now 2k plus 1 also, this with 2k plus 1 minus 9, 2k plus 1. Now you see here how much complication is there to develop a two parallel system for a simple IR filter and a simple order 2. So this I have to represent in this manner. 2k minus 9, I am going to represent with 2 into k minus 5 plus 1. Similarly, this 2k minus 8 with this. Now this is the original system. This A is the source, B is the destination output Y, this C is this adder, and D is multiplier. So here, in order to get this Y of 2k, Y of 2k is B0. This is Y of 2k. This 0 suffix represent 2k, 1 suffix represent 2k plus 1. This is the point where I will get Y of 2k. And this is the point where I will get Y of 2k plus 1. And C elements are adders, D are multipliers. Okay, that is the notation here. A source. This will give the x of n. X of 2k, x of 2k plus 1. A0 will give x of 2k, A1 will give x of 2k plus 1. This C0, C1 are adders, D0, D1 are multipliers. Okay. So if I take Y2k, this is Y2k to generate Y2k. What is the expression? A times Y of 2 into k minus 5. This is Y into 2 of k minus, this is 2k plus 1 with delayed version of 5. This is Y of 2k plus 1. This one, you pass through the 5 delays so that you will get the first term. And this in this D0 you multiply with A so that this entire term will be generated here. That you add with A0 give x of 2k. That sum will be your y of 2k plus 1. Similarly, to get y of 2k plus 1, this y of 2k signal delay by 4. Y of 2k signal is this, delay by 4 units, and you multiply with a, in this d1 multiply with a, this will be added with y of x of 2k plus 1. This is a lot of computation is there. So in order to have this parallel processing system for the iterative system in an easier manner, so we will follow a theorem called unfolding theorem. If I follow the unfolding theorem, whatever the complexity of the system is, I can easily obtain the parallel processing system of iterative filters. So you see this algorithm states that, so if there is a node U in the original DFG, so you have to use for a J parallel processing system, J nodes will be there. Like here, this C is adder, D is multiplier. For two parallel processing system, we have two adders C0, C1, two multipliers D0, D1. If it is three parallel processing system, three C's will be there, three D's will be there. So in general, the computational block for L parallel processing system will be L. So here I am taking J parallel processing system. So J nodes of U will be there. What is this node? It can be adder, multiplier, or any computational block. So what does this unfolding theorem state this? If there is a edge from U to V in the original DFG with W delays, in the J unfolded DFG, Ui will goes to V of I plus 1 percentage of J with I plus W by J floor function number of delays. If I consider the same previous example, the same thing. So between C to D, how many delays are there? 9 delays. Now, in the two unfolded DFG, so we have two C's, C0, C1, two D's, D0, D1. So whether C0 will goes to D0 or D1, that will be decided by this formula. So I is 0, C0, if I consider C0, U is C. So I is 0. And V is D, I plus W percentage of J. W is, I is, for C0, I is 0. And W is original number of delays from C to D, which is 9. In original system, we have 9 delays. And if I consider C0, I is 0. So 0 plus 9 percentage of J. J is, this is two unfolded system. So J is 2. So what is the percentage means? This is remainder. So this is 9 plus 0 percentage of J is 2. So which is equal to 1. Remainder is 1. So this C0 will goes to this V suffix of this one, which is 1. And with how many delays? I plus W by J floor function. I plus W is 0 plus 9 by 2 is that is 4.5 floor function. Floor function means even if it is 4.9 also, we will make as 4. That is floor function. 4.999, 4.9999 also we will take as 4 only. So this is 4 delays. Similarly, you can check for the C1. In case of C1, I equal to 1, W is same 9, J is 2. So C1 will goes to D0 with 5 delays. So remaining, if there is no delay here, 0 will goes to 0 with 0 delay. 1 will goes to 1 with 0 delay. So this is the unfolded DFG. This is same as the previous one. So which is manually found to do, it's complicated. If I follow this unfolding theorem, we can easily obtain the parallel processing system of iterative filters also easily. Now what are the applications of this unfolding? So by doing unfolding, many of these 5G communication and all, we have lot of unfolding systems because we have to increase the throughput. So one is sample period reduction, as I have told, we can increase the throughput. Another is we can have the parallel processing system. As I have told, parallel processing is subset of the unfolding. We can derive the parallel processing system by performing the unfolding operation. So this sample period reduction also here, so in two cases, we cannot achieve this sample period which is equal to iteration bound. As I have told, iteration bound is the bound beyond which we cannot increase the throughput, even if you have the infinite resources because of the feedback path. In case of non-iterative systems, if I have infinite multiplies infinite adders, infinite resources, I can go up to the infinite throughput. Whereas here it's not possible. So the highest iteration bound that you can achieve is the sample period. There are two cases where even if this sample period we cannot achieve as iteration bound. So one is if this iteration bound is non-integer fractional part we cannot achieve, but using this folding, unfolding we can achieve. Okay, this I have given here the examples. So there are two cases where Ts is equal to T infinity is not possible, but using folding it's possible. I'm not going into the more details because I have a lot of topics actually. So there are several applications of this unfolding. So we can obtain the parallel processing system also. So in this parallel processing also we have bit level serial processing, bit parallel, digit serial. So we have published a lot of papers on this also. So there is another technique called retiming. So retiming is also another transformation technique which is used to change the location of the delay elements. So without affecting input-output relation, as I have told, you perform whatever the transformation is, but you have to make sure that the input-output characteristics, that is the functionality, should remain same. Okay? For example, if I take this IAR filter, what is the expression for y of n? X of n is one input, and this y of n you are taking through the delay. So y of n minus 1 into a, you are adding to this one, and this is two delays, y of n minus 2 into b, you are adding to this. So total expression for this y of n is x of n plus a times y of n minus 1 plus b times y of n minus 2. This is the expression for this. But here what is the critical path? The longest delay free path is from this multiplier to this adder. So this is the multiplication time is 2 units. This the value within the parenthesis is the computation time. The addition value, the addition computation time is 1 unit. So here there is no delay. So this is critical path. So the critical path time here is 2 plus 1, 3 units of the time. What does it mean? If I feed the first sample, after 3 units only I can feed the second sample. I have to wait for 3 units. Now what I am going to do is, I will remind the functionality, but I am going to change the delay locations. So what I am doing here is, this is retimed version. I pull this register, delay here, and I will place the delay here and here. Now what will be the functionality? Functionality remains same. You can easily check that. So this Wn, you delay and then add, or you add and delay, both will be same only. You can easily see that the expression for y of n here and here both are exactly same. Even in the pipelining there will be some delay, latency will be there, but in retiming there is no latency also. Exactly this y of n's are same. You can easily check from here. But now compared to this, what is the critical path of this one? Because now one delay came here. So from here to here delay is there, here to here delay is there. Only between these two adders there is no delay. So critical path is, this is 1 plus 1, 2 units. For this system, the critical path is 3 units. For this system, only 2 units. Means if I feed the first sample, after 2 units itself, I can feed the second sample. So as far as the speed is concerned, the second system is operates at more speed than the first system. What is that you have done? Only just changed the location of this delay element. Here delay was there. You pull this delay and you have placed the delay here and here. This is what is called the retiming technique. In the retiming technique, you have to properly choose the location of the delays so that the critical path will be reduced. Again, here also similar to that pipelining, if I take the complex system, how to choose these delay locations without changing the functionality. Okay? One important point is you have to make sure that the functionality remains same. Okay. So that is difficult task. That is why if I take the complex system, here also I have some rule to place these delays, where the delays has to be placed and where the delays has to be removed. Okay. For that we will follow some sort of cut set retiming, like cut set pipelining. Here also cut set retiming. So here what we will do is we will divide this entire graph, this is graph, into two subgraphs, G1 and G2. This is G, I'll divide into two subgraphs, G1 and G2. For all the, these are the edges going from G1 to G2 with V1, P2, Pj delays. These are the edges going from G2 to G1 with the Q1D, Q2D and so on. So what we are going to do is, I am going to add K delays using this formula for all the edges going from G1 to G2. And the same number of delays I am going to subtract from G2 to G1. As the result of that, what happens is, we'll get the functionality remains same. At the same time, if I properly choose this cut set, then I can reduce the critical path, thereby I can increase the throughput of the system. Here I have taken the example of this one. So if I use this formula, we'll get K as 1. So if I choose this cut set as this cut set, this is G1, G2. If I remove these three edges, this edge, not red one, this black one, cut set. This edge, this edge, this edge. If I remove, this becomes two disjoint graphs. Now, for all the edges that are going from G2 to G1, there is one edge with delay. You subtract one delay, so that this becomes 0 delay. And for all the edges going from G2 to G1, you add one delay. So this delay. So that will reduce the critical path. Now critical path is 2 to 1. This is also 1 unit, 2 units. So this is how we can choose the proper location of the delays, where the delays has to be subtracted or deleted or removed, and where the delays has to be inserted. Okay. So that we have to follow this cut set ruling. And there is some other algorithm also there for finding the exact location of the delays. So see how we can, by just replacing the delay positions, we can increase the throughput of the system. Sometimes we lose a slow system and then you apply the retiming, we'll get a lot of benefit in terms of critical path and throughput. If I consider this, for example, 100 stage lattice filter. This is the example of a lattice filter. You might have studied in DSP. So this lattice filter will be very much useful in signal processing, especially in speech processing. So you see the stage 1 consists of 2 adders, 2 multipliers. These two are multipliers. These two are multipliers and these two are adders. And similarly, these two are multipliers, these two are adders. There is a symmetry actually. Between stage 1 to stage 2, there is a delay. This stage 2 is exactly same as stage 1. So there is a symmetry between different stages. So you see the given 100 stage lattice filter. Now what is the critical path of this one? This is one interesting problem. So we know that the definition of the critical path is the computation time of the longest delay free path. So what is the computation time of the longest delay free path? Here there are delays, but here along this path there is no delay. So if you see here, interestingly, you start with this multiplier, this dotted line. You go in this direction, there is no delay. You go in this direction, no delay, no delay. So go in this direction, no delay. So total how many multipliers and how many adders are there along this path? You can easily see that 2 multipliers, 101 additions. You can easily verify. This is one multiplier, this is one multiplier, and along this path, this is also another adder. Along this 100 adders are there, this is another adder. This is the critical part, dotted line. From here to here, the dotted line. So total number of multiplications are 2, additions are 101. Now what I am going to do is I will slow down the system. Instead of using this delay, single delay, I will use 2 delays. So this is slightly slower than this one. Now I will apply the retiming. So in the retiming, what you have to do? So from this edge, you remove one delay and you place one delay here. You remove one delay here, you place here one delay here. So after this retiming, what happens? These 2 Ds I have distributed between 2 edges. One I have removed here, one I have added here. Now we can see that the critical path will be, so starting from here to here, here, here. So there are delays, so I cannot go to the second stage. So we can see that now the critical path time is 2 multiplication, 2 additions. So if I take the multiplication time as 2 units, adder as 1 unit. So this total is, in case of original lattice filter, it was 105 units, whereas in case of retimed filter, it is 12 units only. There is a great reduction in the critical path time, thereby great improvement in the throughput of the system. So this is a main example of this retiming. So the opposite operation to that of this unfolding. Unfolding is actually we have a single block, I have a replication of the blocks, so that I will process more samples, thereby I will increase the throughput. Okay, this will be required for high speed applications such as 5G and all. Whereas in applications like as I have told in biomedical, I don't need this high speeds. What is required there is I require less area, less power. Okay, so in that case we will use folding. Folding is reverse process to unfolding. So in case of unfolding, I have one multiplier, I will use 3 multipliers. I have one adder, 3 adders. Whereas here I have 2 adders, I will implement with only single adder. I have 4 multipliers, I will implement with only single multiplier, so that I can reduce the area power. Okay. But what about the functionality? So how do you make sure that the functionality remains same? If I take a simple example of a 2 adder circuit, Y of n is simply an plus bn plus cn. I require 2 adders. I can implement the same y of n is equal to an plus bn plus cn using only single adder. But I require one delay. I don't care about this delay. So here this is the switching arrangement. So this circuit also performs same as that of this. But here this requires 2 adders. This requires only 1 adder. How to perform this one? This operation will be clear from this table. So what I am going to do is, in 0th cycle, this 2L plus 0 represents what? 0th cycle, this switch will be connected here. In the first cycle, this will be connected here. Again, second cycle is equivalent to 0. Second here, third here, fourth here, fifth here, and like that. Similarly here, this switch will be connected here at 0th cycle, 0, 2, 4, 6 and so on. And this switch will be connected here at 1, 3, 5 and so on. So initially, I'll make this switch here, I'll make this switch here, so that here this AN and BN will be added. This is in cycle 0, left adder input, this one is A0 and top one is B0. And system output I am not taking, I will take initially at every, because I have not performed this one, 2L plus 0, even if we switch, initially I will clear this D flip-flop so that output is 0. Then in the first cycle, so what will be this? After this one delay, after this delay, this adds A0 plus B0, so that will be supplied here. Now this switch will be moved to here. So adder left input will be A0 plus B0, that comes from this adder and this delay element. Then C0 is available here, because this will switch to this. And second clock cycle, A1, B1, but the output will be, this will be closed. So A0 plus B0 plus C0. So only thing is, this is the speed of this one is half of that of this, but the computational complexity is also almost half. So that this type of relation is very much useful for low power and low area applications. 2 multipliers, 2 adders we are going to implement with single adder. So like that, even if you take this circuit which is consisting of 4 adders, 4 multipliers. This is a famous biquad filter. 4 adders are there, 4 multipliers are there. I am not going into the details analysis of this one. This I can implement with only single adder, single multiplier. You see here. Instead of using 4 adders, 4 multipliers, I am using only single adder, single multiplier. But we require some sort of the switching arrangement. So the switches can be implemented by using a multiplexer. I have 4 options. I have to choose one. So we can implement by using the multiplexer. So these are about this the architecture optimization techniques such as pipelining, parallel processing, retiming, folding and unfolding. So this is one part of this presentation, but all this requires the multipliers. Okay. Multiplier is I'm going to discuss in the coming slide that multiplier is a computationally extensive operation which requires lot of gates. There are some realizations which does not use the multipliers, which are called multiplier-less architectures. So we have quadratic based and DA based architectures. So I will discuss the multiplier-less based architectures after a break of 10 minutes.
Dear participant, right now it's a 10 minutes break. After 10 minutes, the session will be resumed.
Shall we start?
Yes, sir. Please start, sir.
Okay, the next topic is Cordic based signal processing. As I have told, the multiplayer complexity is large. It is computationally intensive operation. So there are some architectures which does not use the multiplexer. So one of such relation is Cordic. Cordic is actually basically the full form of the Cordic is coordinate rotation digital computer. So this CO is taken from this coordinate, R is taken from rotation, DA is taken from the digital, and C is computer. So this is actually a smart way of computing this cos theta for any arbitrary angle. Initially in olden days, in 1950s and all, there were no calculators. So if you want to compute cos of say any arbitrary angle 32 degrees, cos 45, cos 60, 30, these standard angles we know the values. But if you want to compute cos 32, cos 47 and all arbitrary angles, there are no calculators. So that time the a mathematician called Older, he searched the literature and he developed a algorithm which is called Cordic. So as for this, Older, he defined the universal angle alpha theta, alpha k as tan inverse of 2 raised to the power of minus k. And this alpha 0 is k is 0 means 2 tan inverse of 2, which is 45 degrees. And alpha 1 is, if you compute this one using this formula, 26.5, 14, 7.5, these are the alpha angles. So alpha 0 is greater than, alpha 1 is greater than, so on. It will go up to 0. If I take the infinite iterations, it will go up to 0. And here this alpha angle is between 0 to 90 degrees. If I know the values, all the values from 0 to 90 degrees, 90 above also you can represent in terms of 90 plus theta. So you can find out those values also. That was the basic idea behind this development of this algorithm. So his claim is that you take any arbitrary angle. This can be expressed as sum or subtraction of these universal angles. These are fixed. This is according to this formula. So k is 0 means 45, k is 1 means 26.5, 14 and so on. So his claim is you take any angle theta, we can express as I is equal to 0 to infinity. If I add up to the infinity, we will get 100% accuracy, where this delta is plus or minus 1. And delta 0 is 1, delta I for I is not equal to 0, means delta 1, delta 2 are plus or minus 1. So depends upon whether this is plus or minus, depends upon whether the sum is greater than or less than theta. For example, if I take say theta is equal to 64. So now to represent this 64, so I'll start with alpha 0. Always alpha 0 is positive. Delta 0 is 1. So alpha 0 is 45. The next angle we have to add or subtract. The next angle is 26.5. Next angle you have to add or subtract. That depends upon whether this 45 is greater than or less than 64. Here because this 45 is less than, next angle has to be added. By adding these two, whether this sum is greater than 64 or not. It is greater than 64, so I have to subtract the next angle. The sum is again still less than 64, so I have to add the next angle 7.125. Even if I use up to the 5 iterations, you are getting 64.6, it's more than 90% accuracy. If I go up to infinity, you will get 100% accuracy. But here, even if I use few iterations, like here I have used only 4 iterations just. So I got 64.6. You take any angle this, between 0 to 90 degrees, any arbitrary angle, you can express as sum or subtraction of these standard angles. That is his claim. Now, the signal processing people, they want to fabricate FFT on the IC. How to realize cos theta sin theta in hardware? That was the interesting problem that time. How to realize the cos theta? Cos theta I cannot realize in hardware. So in case of computer programs also, if you want to implement cos theta, I'll use the lookup table. Theta varies from 0 to with a resolution of 0.1 degree or 0.001 degree. So I'll store the values in the lookup table and I'll pick up that corresponding value. But how to implement this cos theta exactly in the hardware? So for that, so they found this quadratic algorithm, and finally they succeed, and they implemented this x cos theta, y sin theta. So all these type of x cos theta, x sin theta terms using hardware, that too without multiplier. After the development of this becomes very popular. So in many of the applications, like especially in communication applications, if I take the quadrature component and in-phase component, that will be in this form only. And if I take this nowadays this machine learning algorithms, we require sigmoid, we require Rayleigh function. So this sigmoid and all, it requires the cos h theta sin h theta. That all those things can be implemented by using the quadratic without multipliers. So the basic principle of this quadratic is, you take a vector xy. This is a distance of x from the x-axis, y from the y-axis. If I rotate this xy by theta, if I call the resultant vector as x dash y dash. So what is the relation between the x, y, x dash, y dash and this theta? This is, you might have studied in your elementary mathematics in higher secondary and all. Direction cosines, this one. So this x dash, y dash is nothing but cos theta minus sin theta, cos theta into xy. That is basically in quadratic we are going to input theta. This matrix is cos theta minus sin theta. So output will be, if I multiply x with cos theta, y with minus sin theta. So this output will be x cos theta minus y sin theta. Second output will be, the second row with this xy is x sin theta plus y cos theta. This is your x dash y dash. This x dash y dash is nothing but, in terms of this x dash is equal to x cos theta minus y sin theta, y dash is equal to x sin theta plus y cos theta. Now what we are going to do here is, initially we will rotate this xy by alpha 0. This alpha 0, because any theta can be represented in terms of this alpha 0 plus or minus alpha 1 plus or minus alpha 2 and so on. So initially you shift this xy vector by 45 degrees, which is alpha 0. Then the next angle alpha 1, either in the forward direction or reverse direction, depends upon whether the sum is less than or greater than theta. So like that you rotate this until you will get a finite precision. So normally here if I go up to infinite iterations, we will get 100% accuracy. But for practical purposes, you can use less number of iterations. Even as I have told, 4 or 5 iterations also will be enough. It will give more than 90% or more than even nearly 99% accuracy. So that is why what I am going to do is, now theta, instead of implementing with infinity, I will use only m iterations only. So if I take here this cos theta as common, we will get 1 minus tan theta 1 xy. So what I am going to do here is, this is the complete diagram. So initially I will give alpha 0. Initially I will give x0, y0.
Hello, Mr. Professor Shaik, you are not audible. Hello. Hello, Abid.
Sir,
Uh,
there is some problem in the
okay,
internet from his
okay,
side.
okay. We can message.
Sorry, there was some network issue. Now, am I audible?
Yes, sir.
Yeah. Screen is visible?
Yes, sir, visible.
Okay. So, initially you take x0, y0, you rotate by alpha 0. Alpha 0 will be in the forward direction because here this alpha 0 is, delta 0 is 1. So, this is actually alpha 0, delta 0, alpha 0 plus delta 1, alpha 1 plus 1 up to. So, this delta 0 is plus 1. So, initially you rotate by alpha 0 in the forward direction. Yeah. So total theta, actually total angle that I have to rotate is theta. So this theta I am going to rotate in micro angles. Okay. Because we know that theta is equal to delta 0 alpha 0 plus delta 1 alpha 1 so on up to infinity, but finite precision I am taking n minus 1 or 0 to m minus 1 is total m iterations. Okay. So this is delta 0 alpha 0 plus or minus delta 1 alpha 1 plus or minus 1 up to delta m minus 1 alpha m minus 1. Out of this delta 0 is positive. So initially I will rotate by alpha 0 which is 45 degrees. Then I will see whether this 45 degrees is greater than or less than the total angle that is to be rotated, this theta. If it is greater, I will move in the forward direction, otherwise I will use in the return direction. So like that, after m iterations using this formula, I can reach this xm minus 1, ym minus 1. The total angle will be theta now. Is it clear? So to get this, to get from one stage to another stage, this is the mathematical expression. If I take I plus 1 angle, I plus 1 angle, xi, yi. If I take the input vector as xy, yi, output vector is xi plus 1, yi plus 1. What is the corresponding matrix with which you have to multiply ith stage to I plus 1 stage? So like that I'll get from 0 stage to 1, 2, 3, so on to m minus 1 stages. This I varies from 0 to m minus 1. So in general, ith stage to I plus 1 stage, the mathematical expression is this. Because here, this is cos theta minus sin theta, cos theta. So this is input vector, this is output vector, total angle is theta. Now this theta I am going to take as micro angles. So this is the expression for the I plus 1, xi plus 1 is equal to xi into cos alpha minus r plus sin alpha, y of I plus 1 is equal to xi sin alpha plus or minus and yi cos alpha. And if I take the cos alpha as common, I will take this at the end. So then this is 1 plus or minus tan alpha 1. But what is this tan alpha k? as per this Holder's algorithm, the initial starting assumption is alpha k is tan inverse 2 raised to the power of minus k. What is tan of alpha k? 2 raised to the power of minus k, which is shift operation. This is very interesting formula. This tan alpha k, this tan alpha 0 and all, we are going to represent with, this is tan alpha I is nothing but 2 raised to the power of minus I. Now what happens to this xi plus 1? Xi, this is xi plus or minus tan alpha I, which is equal to 2 raised to the power of minus 1. So this xi plus 1, yi plus 1 can be obtained from xi and yi using just simply shift operation, add operation. This is add or subtractor. Is it clear? So this is interesting topic. This is this is input xi stage, yi stage. The input is alpha I and theta I. Output is xi plus 1, yi plus 1, theta I plus 1. So this can be obtained by using only just the adder subtractors and then shifters. So if I have m such blocks, this is from, if I feed here x0, y0, we'll get x1, y1 using this circuitry. Then x1, y1, I will feed to another such a quadratic block, I will get x2, y2. So like that, if I go up to n minus 1, I will get total angle is theta and the final output will be this x cos theta minus y sin theta, x sin theta plus y cos theta. So this is the quadratic unit where without using any multiplier, I can obtain x cos theta, y sin theta and x sin theta plus y cos theta, this angle is. But inside this quadratic we have m such blocks, m such blocks. So initial block, first block, the input is x0, y0, theta 0, alpha 0, output will be x1, y1, theta 1. You give this as input for the second stage. Again we have this adder subtractors shifters. We will get x2, x1, x2, y2, theta 2, then x3, y3, theta 3 and so on. You go up to x of m minus 1, total m stages. So if we add those angles, you will get which is approximately equal to theta. As I have told, after 4 iterations itself we have got more than 90%. After by properly choosing the m value, we can obtain up to the 99% accuracy. Now if I take this quadratic based relation of FFT algorithm. So in the previous, the techniques I have used these filters only. As I have told, signal processing means filters and transforms. Okay. Here, because in FFT we require trivial factors. Trivial factors will be of the form of x cos theta, x sin theta. So this is very, perfect, match to implement the FFT architecture. So if I take the FFT, we have the flow diagram. So in that, the basic flow is this. You have to multiply with, this is trivial factor, AB, you multiply this with trivial factor, then you subtract this, we add this, you will get A dash, B dash. So you will be having a lot of this butterfly throughout this flow diagram. So if I want to implement this butterfly, how many quadratic blocks are required? Input is AB, output is A dash, B dash. In between you are multiplying with e raised to the power of minus j 2 pi nk by n, and this is subtraction, this is addition. This is the basic butterfly. So I am considering the basic butterfly. If I implement this using several such butterflies, I can implement the FFT. So here you can easily see that this A dash is nothing but A plus this A is passing A plus B into trivial factor. I am calling this entire thing as theta. A plus B raised to the B into e raised to the power of minus j theta, and B dash is A minus, this is minus is there. So this is basically A dash B dash expression in terms of AB, where theta is this value. So how many quadratic blocks are required? So what is given? AB are given. You are given AB and theta is given. I have to find out A dash B dash using hardware. This is the, so A dash, if I take A plus B e raised to the power of minus j theta, if I expand this in terms of real part and imaginary part, A is having this AR is real part and J, A is the imaginary part. BR is the real part, imaginary part. And e raised to the power of j theta is cos theta minus j sin theta. So after simplification, you will get the total real part of A dash is this, imaginary part is this. Similarly, B dash is this, imaginary part is this. Now, interestingly, we can have a single codic to implement a single butterfly. So here, what does this codic will give? As I have discussed in the earlier, if I give theta as the input and xy as the mean inputs, output will be x cos theta minus y sin theta, and this output will be x sin theta plus y cos theta. Now what I am going to make is to implement this A dash, I will make this x is equal to bi, y is equal to br. So what will be this value? X is bi, so bi cos theta, this bi cos theta will be generated here, and y is br, so minus br sin theta, minus br sin theta. This sum term will be generated here. Similarly, if you want to generate this A will be added outside to generate br cos theta plus bi sin theta. What will be output here? X is bi, so x is bi sin theta is this, bi sin theta, and y is br cos theta. So this entire this term will be generated here, this term will be generated here. Only you have to add with a and bi. You can use simple adders outside this. You add here using a, so that you will get imaginary part of a dash after adder here, and you will get real part of this a dash after adding here. Similarly, you can use to implement b dash, I require one codic unit, or you can use the same codic unit to represent the b also. If I give the BA and BR as inputs, BA and BR are the inputs, X will act as BA, Y will act as BR, outputs will be in this form. This AR dash, AI dash, we require adders and subtractors outside, but using single block only. PQ, if I call this as Q, P is equal to BR sin theta plus BI cos theta, Q is BR cos theta minus BR sin theta. So by adding and subtracting these values only, we will get both the real part of A, B, imaginary part of AB. So this. You can see here that BR cos theta plus BI sin theta is this. This BI cos theta minus BR sin theta is this. This entire thing we are going to generate here. As a result of that, only single codic block is enough to generate this output A dash B dash from AB, which is the basic butterfly unit. This is the implementation. This is the implementation using single codic processor, but we require two adders and two subtractors outside. So given the input A and B, that is the real part, imaginary part of A, real part, imaginary part of B, you will get real part and imaginary part of A dash, real part and imaginary part of B dash. This is a great achievement. So you can use a single codic unit to implement a butterfly. And if you take the 8-point FFT, 8-point FFT, total how many butterflies will be there? So we will be having 4 butterflies in each stage, 12 butterflies. So using 12 codic blocks, you can implement 8-point FFT. If you want to implement by using multipliers and adders, you require huge number of multipliers and adders. Whereas here, this is multiply less architecture, and we can reduce the complexity by a great amount. This is one application of this codic. Even you can implement this DCT, and also this having a lot of applications. Starting from 1952 to till date, there are many applications of this codic, and there was one paper published which is called 50 years of the codic. Over the 50 years of the codic, this codic has been used in communication, in robotics, in signal processing. A lot of applications are there. So the second, the multiply less architecture is distributed arithmetic based signal processing algorithms. So this is two's complement representation. Here we are going to use in distributed arithmetic. This is something like signed arithmetic. We are going to use signed arithmetic because the input data in real-time system, it can be a positive value or negative value also. So in order to represent the negative numbers, we can represent 1's complement and 2's complement representation, but 2's complement is famous because of the two advantages. One is, even if you have the intermediate overflow or underflow, you can neglect if the final result is within the limits. That is one of the advantage of this 2's complement representation. And if I take this W bit representation of A is a number, W bit number representation. In fixed point, signed 2's complement representation is this. W is the number of bits used for representing the A. W minus 1 is the MSB bit, followed by the dot binary point, AW minus 2, so on up to A1, A0. Total W bits. Each A0, A1, so on up to AW minus 1 can be either 0 or 1. After MSB bit, there is a binary point. So this AW minus 1 is a sign bit. For positive numbers, this is 0. For negative number, this is 1. And the remaining values are AW minus 2 to A0. They represent magnitude. So this is binary form. Whereas in decimal form, if you want to get the decimal value, we know how to convert this binary number into decimal number. This before this binary point, this AW minus 1 is there. This into 2 raised to the power of 0. The weight is 2 raised to the power of 0. Okay. If this is positive number, it will be 0. So 0. If it is negative number, minus 1. So this is minus of this AW minus 1. If this is 0, minus 0 or plus 0 does not matter. 0. If it is 1, represent that minus 1. Minus 1 into 2 raised to the power of 0. And whatever the weight of this AW minus 2, which is 2 raised to the power of minus 1. After this binary point, the powers of negative powers of 2 will be the weights. So AW minus 2 into 2 raised to the power of minus 1, AW minus 3 into 2 raised to the power of minus 2, and so on. You can see here that if I is equal to 1, which is AW minus 2, the power is 2 raised to the power of minus 1. AW minus 3 is 2 raised to the power of minus 2. And the last weight will be A raised to the power of minus of W minus 1. So in this representation, the range of the numbers that can be represented is the minimum value is minus 1 and maximum value is a negative number which is minus 1. And the maximum positive number is 1 minus 2 raised to the power of minus of W minus 1. This is clear from this example. So unlike the unsigned numbers W bit means what will be range? It will vary from 0 to 2 raised to the power of W minus 1. If it is 8-bit number, 0 to 255 numbers, you can represent. Whereas here, this is, range is minus 1 to 1 minus 2 raised to the power of minus of W minus 1. If I consider the 4-bit by 4-bit multiplier, as I have told, the multiplier is a computationally intensive block. So if I obtain the architecture of this 4-bit by 4 multiplier, so you can see the how much complex the circuit is. So this is A3 dot A2 A1 A0, B3 dot B2 B1 B0. You have to perform AB basically. So A into A I am taking directly and B I am considering the binary equivalent. B3 minus B3, as I have told here, this is the binary form, this is decimal form. This is decimal form is minus AW minus 1 and AW minus 2 into 2 raised to the power of minus 1 plus 1. So the binary representation of B is minus B3 plus B2 into 2 raised to the power of minus 1, B1 into 2 raised to the power of minus 2, B0 into 2 raised to the power of minus 3. So multiply this A with B, minus A B3. So this is what is called, this is Horner's rule. So this is minus A B3 and A B2. What is the coefficient of A B2? A B2 should be 2 raised to the power of minus 1. This A B2 is multiplied with only this. A B1 with this and this. So to get to A B0 is total 3. This and this. This 3. It's Horner's rule. So here to get the minus A, A3 bar, A2 bar, A1 bar, A0 bar, which is the 1's complement plus 1. So that will be, this is minus A3 bar plus A2 bar into 2 raised to the power of minus 1, A1 bar into, because this is 0, A0 bar into 2 raised to the power of minus 1, this one is 2 raised to the power of minus 3. This is all actually a lot of computations are there here to realize the 4-bit multiplier. And if you want A into 2 raised to the power of minus 1, this also you have to evaluate. This A into 2 raised to the power of minus 1. So this is A into 2 raised to the power of minus 1 is, you are getting 4 bits. This is what is called the sign extension. You might have studied in your digital circuits. A, if you multiply with 2 raised to the power of minus 1, A3, A3, A2, A1. A0 you can neglect. So if I implement this algorithm, initially A B0 2 raised to the power of minus 1. This is A B0 2 raised to the power of minus 1. You are going to evaluate in this step by step. You evaluate first this, then you add this, you shift this, again you add this, you shift, again you add to final one. So this algorithm, if you want to represent in the table, this is the table representation. This is sign extension. Wherever 2 raised to the power of minus 1 is there, this operation is sign extension. If the input is A3, A2, A1, A0, if I multiply with A 2 raised to the power of minus 1, this becomes A3, A3, A2, A1. If it is A into 2 raised to the power of minus 2, A3, A3, A2, A3, 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 A2. Okay, like that. So this, if I map onto this architecture, we will get this many plus minus blocks. This is nothing but each, this block is full adder. This will represent the full adder type of thing. So we require total 16 full adders to realize a 4-bit by 4-bit signed multiplier, which is of more complexity. Whereas if I use this distributed arithmetic, I require only shifter and adders instead of multipliers. So if I take this distributed arithmetic, this one, so we will consider a two inner product of the two vectors. You take filtering operation, you take the transform operation. So basically inside that there is a inner product only. So if I consider this C as a vector with the C0, C1, so on up to Cn minus 1 elements, X as a vector with the X0, X1, so on up to Xn minus 1. So if I use Y is equal to C transpose into X, what will get? C0, X0 plus C1, X1 plus C2, X1, C2, X2 plus 1 up to Cn minus 1, Xn minus 1. So this we are going to represent in summation notation using this. This Y is nothing but C0, X0 because C transpose. C is here I have shown as a row vector. C transpose becomes column vector. And this X is row vector. So if you multiply this, you will get C0, X0 plus C1, X1 plus C2, X2, so on up to Cn minus 1, Xn minus 1. You see nothing but sum of products or inner product. If you take the filter, we have sum of products only. If you take the transform, sum of products only. So if I implement this inner product realization, then I can easily realize any filter or any transform. That is, we have considered here inner product. And here Xi I am going to represent with 2's complement. As I already discussed, 2's complement will be represented in this manner. Whereas Ci I have taken as it is. I will represent with fixed number. After this manipulation and all, so we will get finally this type of architecture. So here what we will get is we will get Y is equal to simply C7 2 raised to the power of 0, C6 2 raised to the power of minus 1, so on up to C0 2 raised to the power of minus 7. Means this is nothing but shift. 2 raised to the power of minus 1 is shift, 2 raised to minus 2 is shift, and then you add. So this entire this inner product is just transformed into shift and add, shift and add. So if I compute this capital C7, C6, C5 and so on up to C0. So by using shift and add operation, I can obtain the final output Y, which is the inner product. How to obtain this C7, C6 and all? is we can implement this using a lookup table. So this C0 is, to get the C0, I will find out the values of this X0, X10, X20, X30. These are bits. If I take all zeros, we'll get 0. If I get 0001, we'll get only C0. If I expand this, 0010, we'll get C1. 0011, C0 plus C1. If I get all ones, we'll get C0 plus C1 plus C2 plus C3. So this what I will do is I'll pre-compute and store in the memory. So after that, depends upon the input that is received, I will compute this C0. Similarly, C1 also we have similar type of the architecture. The values that we are going to store here is same. The only difference is here this, instead of giving this X00, 10, 20, 30, I will give X01, 11, 21, 31. I will get C1. Similarly, if I give 02, 12, 22, 32, I will get C2 and so on. So C0 to C6, the number of the content that we are going to store here is same. Only if I change the address, I will get C0 to C6. But for C7, there is a negative sign. From C0 to C6, all are positive values only. So I can use the same locations by just changing this address. I generate C0 to C6. But C7, the content that I have to store here will be negative numbers. So for that, we are going to use a logic. You can see here, this is C0 to C. For all four combinations like here. If I give all 0, 0, 0, 0, 0 will be selected, 0, 0, 0, 1, C0 and so on. This is the contents. So this is the logic that I am going to play here. So I will store inside the ROM either positive values or negative values. It is up to you. From C0 to C6, here I have positive values. For C7, all negative values. So what I am going to do is, instead of using another memory for this storing C7, I will use only single memory only. I can store either all positive values or all negative values. All positive values if I store, the same values you have to output for C0 to C6. For C7 you have to complement and then you have to output. Okay. So what I'm going to do, I'll store all positive values. Whenever C7 has to be computed, I'll take the complement of that one outside this memory. You can see here. So here I'm going to give the address lines. There is a multiplexer. This S is the selection line. In one case, the output of this one is current I0. The same will be outputted to the multiplexer. In other case, this is minus sign. Minus sign will be implemented by using 2's complementer. It's represented as an inverter, not gate, but this is actually 2's complementer. So whether I have to take the negative data, 2's complement of the data or the original data, that depends upon the S. So when you have to take the original data, when you have to take the complement of the data, is C0 to C6 the original data and C7 the complement of the data. If I take the 8-bit. So this S I will make as 0 for the first 7 cycles and the 8th cycle I will make as 1. So that whenever C7 comes, it will complement it, will go here. Once if I know this C0 to C7, what you have to do? How do you get output Y? Y nothing but C0 into 2 raised to the power of minus 7, C1 into 2 raised to the power of minus 6, C7 into 2 raised to the power of 0. As you can see here. So initially I'll generate C0 here and I'll clear this shift register. So C0 plus 0, C0 is the output. That will be shifted. In the second clock cycle, what will be the input here? C0 into 2 raised to the power of minus 1 and here C1. So like that, initially I have generated C0, total 8 clock cycles. So this will shift through this shifter 7 times so that it will multiply with 2 raised to the power of minus 7. Because the initial value that I have generated is C0, it will pass through the shifter 7 times. And the second value that I have generated is C1. So how many times it will go through the shifter? 6 times. So like that, the last value that we are going to generate is C7. It will not go through the shifter. The shifter. So this is 2 raised to the power of 0. So after 8 clock cycles, this will accumulate. That is what this is called shift accumulate unit. Shift and it will accumulate. So after 8 clock cycle, will get output as Y. So this whatever this inner product thing that we are implemented by using simply a lookup table or ROM, a multiplexer, and then shift accumulation unit, which consists of adder, delay, and shifter. So you see the entire architecture which implements the inner product. In the sense, it can implement the filter as well as the transform, because both operations are inner product only. The operation involved in the filtering is also inner product. The operation that is involved in transform also inner product. So any of these filters or transforms can be implemented by using this architecture, where we require ROM and then some sort of the multiplexer, adders and shifters. So if I consider the multiplier complexity and the complexity using this distributed arithmetic, so we'll get a lot of reduction in the complexity because of the multiplier less architecture. Even you can reduce this ROM
Sorry,
size.
sir.
Yeah.
Sir, next 10 to 15 minutes we will wind up. Then
Yeah.
there is a 10 to 15 minutes question answer session is also there.
Yeah. I'll end at 9:15 and 15 minutes will be for a question answer.
Okay.
So this actually ROM is the contents, actually the ROM size. Here total we require 2 raised to the power of n. In case of 4 bits, we have total 16 locations. In general, if you have n bits, 2 raised to the power of n locations. Okay. So one of the drawback of this type of realization is the ROM access time. If I increase by one more bit, this is 2 raised to the power of n words. If I use 4 bits, 16 location. If I use 15 bits, it is 32 locations. That is, the number of locations rises exponentially rather than linearly. So because of that, as the number of location increases, the memory access time also will be more. Accessing the memory from the 16 location takes less time when compared with the accessing the memory from 32 locations. This is like in a street, if you have 10 houses, finding a house in 10 houses is easier task when compared with finding a house in 100 house street. Okay. So like that, here if you have the 16 locations, the access time is less. If it is 32 locations, if I use 5 bits, then access time is more. So this memory access time is one of the bottleneck for this DA based implementations. So then people has worked on how to reduce the memory size. So in order to reduce this memory size, so this DA has been modified by a technique called offset binary coding, OBC. So in this, they cleverly represented this, and finally what they found is out of the 16 locations, 8 locations will be having positive values, 8 locations will have negative values. Instead of storing these 16 different values, you store only the 8. The remaining 8 are only the negative sign of the first 8 locations. So that you can take care at the outside of this circuitry, and you can have some additional circuitry outside to add this minus sign to the first half of the locations. So as a result of that, the memory size is half of that of original DA. This is called OBC DA. In OBC DA, the memory size will be reduced by half because of this mirror symmetry. Or otherwise, there is another technique like ROM decomposition. Instead of implementing a single large memory, so you can implement that using smaller memories, so that I can access that in a less time. Okay? This is called ROM decomposition. But the drawback of this ROM decomposition is, instead of using this one 2 raised to the power of n memory, I will use 2 raised to the power of k memories, where k is less than n. But here we require a multi-input accumulator. Here the memory access time can be reduced, but outside this you have to use a multi-input accumulator, which is more complex. Okay. So there is a compromise between the speed and complexity. If you want to have the more speed, you have to compromise on this complexity. So this is another technique to reduce the number of memory locations, thereby to increase the throughput of the system. And if I take the application, as I have told, So in the first, lectures we have discussed the FAR filter, IR filter, then FFT I have used DC, FFT implemented using the Cordic, and here DA I am using to implement the DCT. So DCT is also one of the important transform used in image processing for the video compression. So here also actually lot of mathematics is there. So after doing these things, in fact, this also can be implemented by using these are Cordics. You can use the Cordic or you can use the distributed arithmetic also. So like if I want 8-point DCT, instead of taking 8 by 8 matrix, I can decompose this into two smaller 4 by 4 matrices. Then the inputs we have to, instead of giving the x0, x1, x2, x4, so on up to x7, we can use some adder. So I give this DA. This is ROM 0, ROM 1. Instead of using a single big ROM, I'll use the two smaller ROMs. Instead of using 8 input ROM, I'm using 4 input ROMs so that the memory access time will be less. And followed by the accumulator shift unit. So this will give x0 to x7. This is DCT values. If I give the input as the image samples in time domain, will get output in frequency domain. So here this ROM size will be less, because of that the memory access time is less and the throughput will be more. So see about these various techniques. Actually, I skipped some of the mathematics and all. So based on these works, actually I have done a lot of research and I have published a lot of papers. In fact, nearly some 3 research scholars based on these techniques only, they published, they applied these techniques in various domains, especially in communication, 5G communication, adaptive filters, okay, and DCT implementation. Based on that, we have got these publications. Thank you, and if you have any queries, please ask.
Dear participant, if you have any queries, doubts, please ask.
Hello, sir.
Yeah.
Sir, I have a basic doubt. In your slide number 7, the very beginning, slide number 7, you showed one function. There was an operator called O something, O n square.
Operations, that is operations.
So that's O stands for operation or something else.
Yeah, operations.
And O and bracket n square and
N
O
square is
and
complex multiplications. This one.
yes, sir. So,
This is operations. Total n square operations means here that operation is complex multiplication.
and this operation could be anything like addition or
Addition also you can use O. That depends upon the concept that you have to use. In the case of DFT, that operation is complex multiplication.
complex multiplication.
Professor said, I think it is also referred as in the order of n square. Hello.
Order.
Generally, because order of n square, because maybe the amount of the either whatever the complexity, okay, or that is in the order of n square, I think. Oh.
Okay, probably that actually here that basically that does not mean that is not important. Actually here that n square is the complex multiplication.
Yeah, that is sometime we write order of n or order of n square or something like that. Maybe the complexity could be 5n square. Actually it is 5n square, so it is in the order of n square.
Yeah.
Any other doubts?
Okay, yeah, Professor Sek, do you have any idea about that? The advantage of DA over that codic based design, because both are the multiplier-less. So,
DA
any?
and the Cardic. Actually,
Yeah, yeah.
Cardic will be normally wherever trigonometric functions is there, we'll use Cardic.
Okay.
If it is without trigonometric functions, then DA is preferable.
DAP. Okay, okay, okay. So basically, whenever you have a trigonometric problem, then codic will be better.
Yeah, yeah.
Right, right.
Sir, can we use this distributed arithmetic to build VLSI adders and multipliers, these circuits?
Yeah, yeah. You can implement, this is basically a multiplier you can implement by using distributed arithmetic.
So, and we will hope that it will be faster than those
Yeah, definitely. But
conventional
if you just
conventional.
implement the multiplier, it's not worthful actually. So you take a system consisting of lot of multipliers, you just implement by using DA, then you'll get benefit out of that system. That you can publish somewhere also. But if you take just simply multiplier for experimental purpose, you can do it. As a research problem, you can take some system. There are a lot of algorithms are there involving a lot of multiplications. Okay. So in fact, these techniques you can apply anywhere. So there is some algorithm where we have a lot of multiplications and you want to implement the VLSI architecture. Then you can replace all the multipliers using a DA based blocks and you can reduce the complexity. For the experimental purpose, you can implement a simple multiplier also using DA.
So the main advantage of this DA arithmetic based circuits would be its speed, right, sir?
Speed is because now actually because of the semiconductor technology, the memories are cheaper actually. So this basically consists of the memory followed by some simple adders and shifters.
Yes, sir. Yeah, thank you, sir.
Any other question? I think there is no question. So
Yes, any other question from the participant? I think there is no more question now. Thank you, sir, for providing time to us and presented a very nice lecture in which you covered how VLSI play a very important role in performance of digital system, digital signal processing, image processing application, hardware security, etc. How the algorithm of VLSI can be exploited in the design of arithmetic circuit such that computational time must be increases and reduce chip area and power consumption by considering trade-off between them. Once again, thank you, sir, for accepting our invitation for this atal FDP and provided time for your busy schedule. Thank you, sir.
Thank you. Thank you.
Thank you, Professor
thank you
Sek.
all. Thank you, sir. Thank you all the participants. And for today, the session is end. And tomorrow, at the same time, that is at the 7 p.m. The session is the invited speaker is Professor S.K. Udgata from Central University, Hyderabad, with the title of the Human Activity Recognition using Wi-Fi Signal Propagation. So kindly join on time. Thank you.
Thank you.
For today, the meeting is over.
Thank you.